So the next thing we are going to study is entropy change in ideal gas. Okay, so we are going to understand some of the cases. So this one is the first case, okay, where temperature and volume is going to be changed. Okay, temperature and volume are going to change. Then what is going to be the entropy change? So before that we need to know that this is a topic which is really very important for our numerical point of view. Okay, so while solving the questions from this entropy chapter and availability chapter, there are certain other chapters where we need to understand, where you need to apply the concept of this topic. Okay, so I am going to show you some of the cases where we need to find out the entropy changes, or where or how to find out the entropy changes in some of the cases. Suppose in some of the questions you have given that a process is going on, temperature is changing from here to here and volume is changing from here to here. What is going to be the entropy change? Okay, so this is the case where we can find out in terms of the formula of del S, okay, or the direct equation of del S, okay, is going to be in terms of temperature and volume changes only. Okay, you are going to get initial temperature, final temperature, initial volume, final volume, and accordingly you can find temperature and volume. Similarly, we are going to find some combinations like temperature and pressure, or pressure and volume, something like that. Okay, so till then we need to remember what is going to be the procedure to find out the entropy change. Okay, or after understanding how we are going to find out this, we need to remember the end expression for the application of this expression in our numerical questions. Okay, so let us start the first case. The first case is temperature and volume. That means in terms of temperature and volume, the entropy change is going to come. Okay, so we know that TdS is equal to du plus PdV. Okay, TdS is equals to du plus PdV. So this is the equation we know. Okay, actually the equation was heat transfer is equals to change in internal energy is equals to work, plus work. Okay, so during the time when we found out that the area under the curve in a TS diagram, while projected on entropy axis, that complete area gives us the heat transfer. From that temperature entropy diagram, we have found out that heat transfer can be replaced by this one, TdS. Okay, for reversible process, we have found out that for reversible process, TdS is going to give us our heat transfer, and du and PdV. Okay, so from this, let us divide the whole equation with T. Okay, and if you divide this whole equation with T, this is going to be your ds. Okay, and in place of this is going to be du by T, and this is going to be P by T into dV. Okay, so this is going to be there while you divide it by T. Now if you remember in the last lecture also, we have repeatedly said that what is going to be du is nothing but Cv into dt. Okay, we can easily say that du is equals to Cv into dt. And if you remember that PV equals to MRT for unit mass. So PV equals to, if for unit masses there m is going to be 1, so the answer would be so the remaining equation would be 1 into RT. Okay, so if mass is replaced by 1, that means it is not going to matter here, so we will get PV equals to RT for unit mass. Okay, now here the expression is P by T. Now from this equation, if you take out P by T, what is going to be there? P by T is going to give you R by V. Okay, now this thing we are finding out so that we can replace these values from here to here. Okay, otherwise we will be blind here, because we need to find du, P and T separately. Okay, so we are going to find a simpler solution so that while any question is given, we can find out the solutions, or we can find out the change in entropy very efficiently. So we are going to simplify this. Okay, so if you replace these values, so ds is what? If you replace and at the same time integrate this one. Okay, so integration at 1 to 2 ds. Okay, what is going to be there? Again integration of 1 to 2. What is going to be the value of du? Du is nothing but Cv into dt. Okay, so in place of du we can write Cv into dt divided by t is already there. Okay, plus p by t, in place of p by t there is r by v. So integration of 1 to 2, in place of p by t we are going to put, in place of p by t we are going to put r by v into dv. Okay, now integration of ds, okay, directly integration of ds is given, so integration and directly are going to get cancelled, so s2 minus s1, this is a direct integration, so integration of ds is going to give you s2 minus s1. Okay, integration of ds is going to give you s2 minus s1, and from this cv is going to have a constant value, or you can directly say cv is constant for any substance or any gases or any gas. Okay, for any gas cv is going to be constant, because for liquid and solid cv and cp value are same. So for any gas, since we are mentioning here ideal gas, so for any gas cv is going to be constant, so cv is going to come out. Okay, cv is constant, cv is going to come out. Now the remaining thing is dt by t. Okay, it is similar like the integration formula which you have learned, that 1 by integration of 1 by x dx. Okay, this is the same integration of 1 by t dt. If you remember, the formula had a natural log in it. Okay, so if you put the formula of integration of dt by t, you are going to get ln of t2 by t1. Okay, the integration of this is going to be ln of t2 by t1, and again from this part r is going to be constant. Okay, we all know that r is going to be constant, so if you take out r, what is going to happen? If you take out r, then the remaining thing inside the integration sign, sign is going to be dv by v. Similarly, here we got dt by t. The same thing is here. Okay, just the parameter is changed from temperature to volume. So dv by v is again going to have a natural log term in it. So it is going to be v2 by v1. Okay, so as I have told earlier, the expression which you are going to get, it will be in terms of temperature and volume. Okay, so it is in terms of temperature and volume. If in a certain problem, if it is given that these are the conditions, temperature has changed from there to there and volume has changed from here to here, and R and CV is given, then you can easily find what is going to be the entropy change. Okay, so this is the end expression which you need to remember. Okay, this is the end expression which you need to remember. Okay, so this thing is going to be very important. Okay, in gate point of view. Okay, and to strengthen your concept, this procedure is also required, so that you can see how these formulas are going to help us in terms of solving the questions or understanding the questions. Okay, for understanding the questions, concept is very important, and for solving the problems, this one is very important. So my suggestion would be, if you could remember this end expression very efficiently, you can easily solve the question based on this. Okay. Okay, so the next case is going to be in terms of temperature and pressure. Previously it was temperature and volume, now it is temperature and pressure. Okay, now if you can see, we know that TDS is equals to dH minus VdP. This is another equation which you have found out in the last lecture. Okay, so TDS is going to be dH minus VdP. Okay, now if you see, the similar things is going to happen here. We are dividing this equation, the total equation, by T. So this is the expression which we are getting. Okay, after dividing by T. Now in the previous equation, here we are having du, and here we are having P into dV. Now here it is V into dP. So we are getting here V by T. Previously we had got P by T, so now we are getting V by T. So similarly in place of du, okay, in place of dH we had du, in place of du we had written Cv into dt. Now since it is dH, we are writing Cp into dt. This is the equation which we have found out in previous lectures. Okay, dH is going to Cp into dt. Again here PV, V by T is given. So from this equation, having the unit mass, okay, having mass equals to 1, from this equation of PV equals to RT, we are finding out V by T. V by T is going to be R by P. Okay, now everything is going to be be similar as previous one. If you integrate this ds from 1 to 2, okay, and integrate this dh means what? Cp into dt. Cp into dt divided by t minus of what? V by t. V by t is going to be replaced with the r by p. Okay, integration of r by p dp from 1 to 2. Okay, now in previous case cv was constant and r was constant. Similarly here cp is going to come out and r is going to come out. This is direct integration. This is going to be s2 minus s1. Okay, this is direct integration, s2 minus s1, and in place of this what it is going to be? Cp. Since dt by t, again it is going to have a natural log term which is going to be t2 by t1. Okay, and in place of this it is going to be r into p2 by p1. Okay, so this is the r into ln into this term is going to be r into ln of p2 by p1. Okay, so this is the final expression from where we can find out any of the entropy change in problems where they have mentioned the temperature is changing and pressure is going to change. Then this is the expression from where we can find out the entropy change. Okay, so this is going to be our final expression for solving problems. Okay. Okay, so the next expression which we are going to find out for entropy change, this is going to be in terms of pressure and volume. Okay, this is going to be in terms of pressure and volume. Now, to find out that expression in terms of pressure and volume, first of all, let us consider the entropy change which we have found out in the last board. Okay, that is in terms of temperature and pressure, what we have found out. Let us consider this one. Okay, now we know that R is what? R is equals to Cp minus Cv. We know that R is equals to Cp minus Cv. Now in the next line what we have done, we have replaced R with Cp minus Cv. Okay, we have replaced R with Cp minus Cv. Now this is the expression which is remaining same, and we have in place of R we have Cp minus Cv. In the next line what we are doing, again this expression is going to be same. We have broken down this term inside the bracket. Okay, so this is going to be minus Cp into ln P2 by P1 and minus plus. This minus and this minus is going to be plus Cv into P2 minus P2 by P1. Okay, now from here what is going to happen, if you take out Cp common, what you are going to get inside bracket, you are going to get this minus this, so you are going to get ln T2 by T1 into, okay, I am writing it directly. Okay, so this, if you take Cp common, this will be Cp ln T2 by T1 minus ln P2 by P1. Okay, if you write out directly, then it is going to be ln of T2 into P1 by T1 into P2. Okay, since here is minus, this will be reversed. Okay, the reciprocal of it will come here. Okay, so this is going to be here, and on the other side this is going to be Cv into ln of P2 by P1. Okay, this is going to be the expression. Now if you consider again PV equals to RT, if you consider again PV equals to RT, we are having here P2 by T2 and P1 by T1. Okay, P2 by T2 and P1 by T1, these are reciprocal. Okay, so let us find out what it is going to be while P by T is going to be there. So in place of P by T we can write R by D. Okay, so wherever there is 2 we will put P2 T2. Okay, by R is going to be constant, R by V2, and wherever there is 1 we can easily write P1 by T1 is equals to, again R is going to be constant, in place of V we are going to write V1. Okay, so from this expression we are getting this. That means wherever we can find P2 by T2, we'll replace it by R by V2, and wherever we'll find P1 by T1, we'll replace it by R by V1. Okay, so from here what it is going to be, you can take Cp, okay, ln of what? P1 by T1 is going to be what? P1 by T1 is going to be R by V1. So this is going to be R by V1. Again this is P2 by T2. okay, or T2 by P2. So T2 by P2 is going to be V2 by R. So in place of this you can write V2 by R, okay, and here it is going to be same plus Cv into ln of P2 by P1. Okay, now from here R is constant, so R is going to get cancelled out. Okay, so what is going to be the final expression? The final expression is going to be S2 minus S1 equal to Cp into ln of V2 by V1, ln of V2 by V1 plus Cv into ln of P2 by P1. Okay, so this is going to be the final expression in terms of volume and pressure. Okay, now you can put wherever I mean whichever equation you can apply all of these. Okay, so if in some of the problems it is given, then volume is changing from some place to some place, and pressure is going to change from this value to this value, and this is the expression suitable. Okay, we can find out the entropy change from this equation. If temperature and pressure is given, from this equation, and if temperature and volume is given, then the equation which you have found out in the first board, that would be very helpful to find out the entropy changes. Okay, okay, so the next thing is entropy change for a reservoir. Okay, so before knowing this, we need to find that a reservoir are of two types. Okay, one is source and one is sink. Now previously what we had done, we have a temperature source from where heat has been taken out, and there was a cycle, and after cycle whatever work we needed to get, we have got the work, and the remaining heat was transferred to a sink. Okay, so in those cases we had considered this as a system. Okay, we had considered this as a system. Okay, so whatever the heat it is coming in was considered as heat going into the system. Okay, and whatever heat it is, whatever Q1 or the heat that is coming or that is deposited in the sink was considered as a heat which was taken out of the system. Okay, so this heat was considered as positive. Okay, because heat was going into the system and heat was coming out of the system, that is Q2. Okay, Q2 was considered as negative. Okay, because it was leaving the system. Now if you want to find out the entropy change in reservoir, suppose only for sink you need to find out the entropy change, what it is going to be, you have to consider the source as a system. Okay, whatever the source is there, you have to consider that source is as a system. Okay, similarly in sink also you have to consider the sink as a system. Now whatever the heat that was coming from T1 to this one was positive here. Okay, because it was going into the system. Now if in source you consider this source as a system, okay, then this Q1 is going to be negative because it is coming out of the system. Our system has changed here. Okay, previously our system was this cycle. Now this system has been changed to source and sink. Okay, so at this T1 temperature, and what is source? Source is what we can, source is a thermal reservoir from where we can take out a certain amount of heat or infinite amount of heat, keeping the temperature constant. Okay, so keeping this temperature constant, we are taking out heat Q1. So since now this is our system, so whatever the heat it is we are taking out is going to be negative. Okay, so the change in entropy, we know that change in entropy is what? Change in entropy is dq by t. Okay, dq by t. For reversible process it was dq by t. dq means what? What is the amount of heat transfer? So here the amount of heat transfer is Q1 and it is going to be negative. Sorry, it is going to be negative. Okay, so minus Q1 by T1 is going to be the entropy change for source. Okay, similarly in sink, this is the sink. Sink is what? We can give or we can deposit a certain amount of heat. Okay, so that the temperature of that thermal reservoir is not going to change. Okay, sink is what? It is a thermal reservoir where we can deposit continuous heat and the temperature of heat is not going to change. So similarly T2 is going to be constant, the temperature is going to be constant here. So at that temperature, what is the amount of heat it is giving? It is giving a heat of 2. Previously it was positive, negative. Okay, since it was coming out from the system, now the same heat is going to be positive. because now our system is changed, yes, our system is changed and the heat input we are giving to the system is Q2. So the change in entropy is going to be again Q by T, that is Q2 by T2. Okay, now after that we are going to see entropy change for a finite substance. Okay. Okay, so now we are going to see what is going to be the entropy change for a finite temperature body. Okay, that means whenever a body is going to go through some finite temperature difference, what is going to be the temperature change. Okay, so first of all let us consider that this is going to be our body. Okay, this is our mass and this is our specific heat. Okay, so mass and specific heat is given. Now let us say that this body is having an initial temperature of T initial, okay, or Ti. Okay, now for changing this temperature of this body from Ti to Tf, what is going to be the entropy change? Okay, so we all know that entropy change is nothing but dq by T, okay, or the change in temperature by T. Okay, now what is going to be the heat transfer for changing its body from Ti to Tf? Okay, we all know that this is going to be m into c into dt by T, and this is going to be ds. Okay, now since this temperature, okay, this T is what, at what temperature the body is giving out the heat. Okay, suppose in reservoir we had taken the source as temperature T1, and similarly we have found out ds was equal to Q by T1. Okay, now we have kept this T1 same. Okay, but here we need to integrate it. There we did not integrate it because what? Because the temperature at which the heat has been given out is going to be same. Okay, temperature, and this dt also. Okay, that dt was also not there because temperature was same, but some heat was coming out. Okay, but some heat was coming out, so at that time we did not integrate it. But now this temperature is continuously changing. Suppose it is going from T1 to Tf. For approaching from T1 to Tf, it is going through an infinite number of temperature values in between. Okay, infinite number of temperature values in between it is crossing. So the temperature T is continuously changing for converting it from temperature of T initial to T final. Okay, so we cannot directly write ds. We need to integrate it from point 1 to point 2. That is, suppose point 1 is T initial temperature and final point is Tf temperature. Okay, so we need to integrate this. Okay, so if you take m and c is going to be constant. So if you take out m and c, this is going to be ln T2 by T1. Okay, here T2 is what? T final. So I am going to write here Tf. Okay, and what is T1? T1 is going to be T initial. Okay, Ti. That means your final expression of entropy change becomes S2 minus S1 equals to m into C ln Tf by Ti. This is going to be your entropy change for a finite temperature change. Okay. Okay. So the next thing we are going to read is entropy change due to adiabatic mixing of two fluids. Okay, if two fluids are going to mix, then what is going to be the entropy change? Okay, so first of all, let us take that there is a chamber and we have divided that chamber, okay, in two parts. And at one side there is one fluid with temperature T1, mass M1 and specific heat C1. Okay, and in another chamber it is having temperature T2, mass M2 and specific heat T2. Let us suppose this is T1 is greater than T2. Okay, let us suppose T1 is greater than T2. Okay, now after mixing, neither T1 will go to T2. Okay, neither T2 will go to T1. Okay, so after mixing, what will happen? A final temperature will be there. Okay, final temperature is going to be there. Okay, now we need to find what is going to be the entropy change when we mix. Okay, so what is going to be the specific heat we don't know, but we know that the mass and M1 and M2 will mix to become M1 plus M2. Okay, and the final temperature will be there something Tf. Okay, now that is not going to be the average of these two temperatures because here mass is different. Okay, mass is different, that's why the final temperature is not going to be the average of these two, and the specific heat are also not same. if the mass was same, specific it was same, then we could have said that the final temperature was going to be the average of these two, T1 and T2. But here this M1, C1 are different for both these fluids, so that's why the final temperature is not going to be the average. So what the final temperature is going to be, we will find out, and we will find out what is going to be the entropy change. Okay, so from this, now this is adiabatic. Since it is adiabatic, none of the heat is going to be exchanged with the surrounding. Okay, so every change that is going to happen in between this only. Okay, is going to happen in between this insulated boundary only. Okay, so we can say that heat lost by the hot fluid is equal to heat gained by the cold fluid. After mixing, what it is going to be, since none of the heat is exchanging, that is whatever heat exchange is going to take place is in between the systems only. Okay, so whatever the heat it is leaving to reach final temperature TF, the same amount of heat is only gained by this fluid, or the colder fluid, so that it reaches the temperature TF. Okay, so this is going to be that. So now what is going to be the formula for heat lost? Heat lost is heat lost by this one. Okay, what is the amount of heat lost is going to be M1 into C1 into dt. Okay, or final temperature minus initial temperature. What is going to be the final temperature here? Final temperature is TF. Sorry, this is going to be T1 minus TF. This is the amount. Since T1 is positive, or T1 is greater than TF. Okay, because T1 is a hotter fluid. Okay, or the number one fluid is hotter, so it will leave some amount of heat so that it reach to the final temperature. So it will be T1 minus TF. Okay, is going to be equal to what? Heat gained by the cold fluid. What is the amount of heat gained by the cold fluid is equal to M into 2 into TF minus T2. Okay, now T2 is colder fluid. It will gain some heat so that the temperature will increase to TF. So this is going to be there. Okay, now if you multiply all this, what it is going to be? M1 C1 T1 minus M1 C1 TF. Okay, and here it is going to be M2 C2 TF minus M2 C2 T2. Okay, so this is going to be there. Now if you take M2 C2 T2, this side it is going to be positive, and if you take M1 C1 TF that side, then that is going to be positive. Okay, so the final thing would be M1 C1 T1 plus M2 C2 T2. Okay, it is going to be M2 C2 TF plus M1 C1 TF. Okay, so from here you can easily find what is going to be the final temperature. So what is going to be the final temperature? The final temperature is what? The final temperature is going to be, if you take final temperature common from here, okay, and the remaining part will come in the denominator. Okay, so if you take TF common, what is remaining? The remaining thing is M2 C2 plus M1 C1, and here it is, here what is remaining? M2 C2 T2 plus M1 C1, and T1 is remaining here. Okay, so this is going to be our final temperature. Okay, so what is after mixing of two gases, what is the temperature they have attained? We can easily find out by this formula. Okay, so this is going to be our final temperature. Okay, now after that this thing is going to be very important for solving questions. Okay, now after that we need to find what is going to be the entropy change. Okay, so now we all know that del S universe, okay, or ds universe. Ds universe means what? Ds universe. Okay, ds universe is going to what? It has always been greater than or equal to 0. Greater than or equal to 0, because we have seen that entropy of an universe is never going to decrease. Okay, so if this value is going to be 0, okay, that means there is no entropy generation. But if this value is going to be greater than 0, that means whatever the value which we have got greater than 0, that is the amount of entropy generated. Okay, now del S universe is what? Del S universe is nothing but del S system plus del S surrounding. Okay, del S system plus del S surrounding. Now if you look at here, what you are going to see, you will see that none of the heat is going to be exchanged between system and surrounding, or it is written adiabatic, and for adiabatic the surrounding entropy change is going to be 0, because no heat transfer is going to take place with respect to the surrounding. Only thing remaining is this one. Now system, here two things are consisting of the system. Okay, the number 1 fluid and number 2 fluid. Okay, so the del S system is going to be what? Del S 1 plus del S 2. Del S 1 is what? What is the entropy change in the number 1 fluid, and what is del S 2 is the what is the entropy change in number 2 fluid. Okay, so in the previous board, what we have seen the entropy change for a finite temperature body. Okay, so this one also we can say it is final temperature body. So what was the expression we have found out? We have found out the expression was m into c into ln T final by T initial. Okay, so for this one, that is the hot fluid, what is going to be the expression? This is also a finite temperature body. Only for one I am saying, it is also a final temperature body, and it is going from T1 to T final. Okay, so del S1 is what it is going to be, m1 into c1 into ln of T final minus T final by T initial. Okay, so this is going to be our entropy change for this body. Okay, plus del S2. For del S2, this is also a final temperature. This is also a finite temperature body. That means in this body also entropy change is taking place, and the final temperature is TF. Okay, so what it is going to be, m2 into c2 into ct into ln of T final by T initial. What was the initial temperature? The initial temperature of that body was T2. Okay, so del S universe is going to be your this one. Now we can see that del S universe, okay, the entropy change for universe is going to have some value. Okay, entropy change for universe is going to have some value. Okay, now, and this is the value, and since we have said that del S universe is going to be greater than equal to 0, when it is greater than 0, that means that value which is greater than 0 is going to be the amount of entropy generated. Okay, so here you can say that this is the expression for what is the entropy generated due to mixing. Okay, this is the expression for what is the entropy which is getting generated due to mixing of two fluids. Okay, so now we are going to see a special case. Okay, so we have found out that for mixing of two fluids, this is going to be our entropy generation. Okay, or entropy change, what it is going to be, this is for mixing of two fluids. So as I have told earlier, suppose this is a special case where mass of 1 and 2, that is hotter fluid and colder fluid, is going to be same, which is mass m, and the specific heat is also going to be same, which is C. Okay, so what the del S universe is going to be now? So from here, if you put m1 and m2 is equals to m, then you are going to get m and c1 and c2 equals to c, then you are going to get m into c into ln Tf by T1 plus m into c into ln Tf by T2. Okay, so from here you can take m into c common. If you take m into c common, what is going to be there? It is going to be ln. Now if I write it directly, this is ln, m and c is going to get common. Okay, so ln Tf by T1 plus ln Tf by T2 is going to be there. Okay, Tf by T1 and Tf by T2 is going to be there. So now if you directly write this, then this is going to be Tf square. Okay, Tf and Tf is going to get multiplied, and in the denominator it is going to be T1 and T2. Okay, so after that you can write c m into c into ln of you can write here Tf square divided by root over T1 into T2 square. Okay, you can easily write this T1 and T2 square and root over is going to get cancelled. Okay, I am writing this because so that we can get a whole square. Okay, Tf by root over T1 and T2 whole square. So if there is whole square, or you can directly rub this 2 and you can directly write square here. Okay, Tf by root over T1 into T2. Okay, square. So now this expression is going to be 2 into MC, because this is square, the 2 will come out. Okay, 2 will come before. So 2 into MC of ln Tf by root over T1 and root over T1 and T2. Okay, and since it is M and C is going to be same, M and C is going to be same, your final temperature is going to be T1 plus T2 divided by 2. This is going to be your final temperature. This is going to be your final expression for del S universe. Okay, so this thing I am saying that this is going to be average because this and this. But even if you put these values in your expression, what you have got, you've got the expression that T1 M1 C1 T1 plus M2 C2 T2 divided by M1 C1 plus M2 C2. If you put M1 equals to M2 equals to M and C1 equals to C2 equals to C in the expression of TF, where you did not consider that special case, if you put these special cases there also in formula of TF, you are going to get this value only. Okay, so this is a special case of mixing of two fluids, same mass and same specific heat. Okay, so now we are going to solve some question. Okay, now they have said that a heat engine is exchanging heat with 3 reservoirs. Okay, as shown in figure, find out the heat rejected and efficiency of the system. This is a question from the second law. Okay, so they have said that there is a heat exchanger. Okay, this is the figure they have given. This is the heat exchanger. Okay, and this heat exchanger is exchanging heat with 3 reservoirs. Okay, like this they have shown. So they have told us to find out the what is Q rejected and what is going to be the efficiency of that engine. Okay, now as you can see, this is, if a heat engine is given, then this is going to be our system. Okay, and in this system, temperature of 6 kilojoule is coming into this system. Heat of 6 kilojoule is coming out in this heat engine, and heat of 8 kilojoule is coming out in this engine, and QR is getting rejected to a temperature of 100 Kelvin. Okay, now to solve this question, we have two unknowns here, W and Q. So if there are two unknowns, we are going to have two equations to solve this question. Okay, now for solving this question, let us first consider what is going to be the first law. Okay, so first law is what? First law, this is a cycle. So first law for a cycle is what? Heat exchange is going to be equal to the work change. Okay, the net heat transfer is going to be equal to the net work transfer. Now this is the system. 6 kilojoule heat is coming in, 8 kilojoule heat is coming in. Now heat coming into a system is going to be always positive. So it is going to be 6 plus 8, and QR amount of heat is going to get rejected from the system. Okay, or heat is going to come out from the system, so it is going to be negative. So this is our net work transfer. Again, now W is the amount of work which is done by the system. If work is done by the system, then it is going to be positive, so this is going to be W. Now this is one equation. Okay, now from the second law we have found out another equation. From the second law, what we have found out? We have found out that cyclic integration of dq by T is going to be always 0. Now this is a cycle. Okay, and cyclic integration means, cyclic integration of this would be what? 6 kilojoule is coming out from what temperature? 6 kilojoule is the amount of heat that is getting exchanged. Okay, so 6 divided by the temperature is 800 plus, again this is the amount of heat that is getting into the system. So again this will be positive. So 8 by 600. Okay, again this is the amount which is getting rejected from the system. Okay, that means the dq is going to be negative. So we are putting minus there. So what is the amount of this? This is QR. Okay, which is getting rejected, and at what temperature it is going to get deposited? This is 100. So the cyclic integration is going to be 0. So from here you can easily find out what is the value of QR. So value of QR you can find here is 2.083 kilojoule. Okay, so you can easily find what is going to be your QR, what is the amount of heat rejected. So one answer we have found out. Find out the heat rejected. Okay, the amount of heat rejected we have found out here. Okay, now we need to find what is going to be the efficiency. Okay, now efficiency is what? Efficiency is whatever the work we are going to get. Okay, whatever the work we are going to get divided by what is the amount of heat we are giving as input to the system. Now what is the amount of heat we are giving as input? We are giving 6 kilojoule heat as input and 8 kilojoule heat as input. So together 6 plus 8 is going to give you heat given to a system. Okay, so this is going to be your W out divided by Q in. So Q in is what? Q in is nothing but 6 plus 8. Okay, and W out, we have found out W out here. What is going to be the W out? Okay, or the work that is going to be, we are going to get, the amount of work is going to be this value. Okay, that means 6 plus 8 minus QR. QR value is what? QR value is nothing but 2.083. 2.083 is going to give you efficiency. Now what is the efficiency? If you do this, you will get the efficiency as 0.851 or equal to 85.1%. Okay, so in this way you can solve the question of second law considering two equations. Okay, this is the first law equation and this is the second law equation, and you can easily find out whatever the parameters they have asked us to find. So we have found out the efficiency and heat rejected. Okay, all they have given is these three reservoir they have given, and this figure has been given. So from this heat rejected and efficiency we could find out. Okay. Okay, so the another question is, heat is lost through a plain steady wall at a rate of 600 watt. The inner and outer temperature of the wall are 20 degrees centigrade and 5 degrees centigrade. The entropy generation is what? Okay, so this is one question. So they have given us a wall and they have said that the outer temperature is 20 degrees centigrade and the inner one is 5 degrees centigrade, and a heat at a constant rate of 600 watt is passing through this wall. So what is going to be the entropy generation within this wall? Okay, so entropy generation is what? Entropy generation is what is going to be the net change of entropy which is going to be there. Okay, or the del S universe. Okay, we can say that del S universe. Okay, so what is going to be the entropy generation? Entropy generation is nothing but the entropy change within this system. That means what? The positive change of entropy. The positive change of entropy which we are going to find out. Entropy generation means what? We have said that del S universe is greater than or equal to 0. If the value is going to be greater than 0, that means you are going to get some entropy which is known as entropy generation. So the change in entropy is going to be S2 minus S1 here. Okay, so since it is S2 minus S1, so the equation would be Q by, the Q is going to be same, so Q by T2 minus Q by T1. Okay, now this is 20 degrees centigrade. If you convert it to Kelvin scale, then this is going to be 293 Kelvin. Okay, and this is going to be your 5 degrees centigrade. That means if you convert it into Kelvin, it is going to be 278 Kelvin. Okay, this is going to be 278 Kelvin. So what is going to be the calculation here? The calculation is going to be 600 by what is T2? T2 is nothing but 278. Okay, minus what is again Q is 600. What is T1? T1 is 293. Now if you calculate this, you are going to get 0.11. Okay, that means the 0.11 watt per Kelvin. This is given in watt. The Q is given in watt. Okay, and the temperature below is in Kelvin. So the answer which you are going to get is going to be in watt per Kelvin. Okay, so this is the way entropy generation is calculated. Okay, so the next thing we are going to read is entropy change during phase change. Phase change means what? Whenever a substance is converting it from liquid to solid, or solid to liquid, or liquid to vapor. Okay, something like this. So phase change is nothing but the processes of condensation, evaporation, etc. Okay, or suppose you are taking some of the water and you need to evaporate that whole water. So what will happen, you will first need to get into 100 degrees centigrade. Okay, then this body will collect some of the latent heat, and keeping that temperature same, all the water is going to get evaporated. Okay, that means during phase change the temperature remains constant. Okay, because the 100 degree centigrade is the boiling point of water. Okay, boiling point of water. So that means what, keeping that 100 degree constant, they will take some latent heat, and with the help of that latent heat they are going to get evaporated, but temperature is never going to get settled. Change. Okay, temperature is never going to get change. So during the phase change like evaporation, condensation, etc., you can directly say that what is the amount of heat that is getting exchanged during condensation or evaporation is the latent heat. Okay, is the latent heat. So this is the amount of heat that is getting exchanged during phase change, and at what temperature? At what temperature? Again, the 100 degree temperature of that water is known as saturated. Okay, saturated temperature means what? At that temperature, at saturated temperature, it may be saturated vapor. Okay, so in that saturated temperature is nothing but when it is the temperature when just all of the water is going to get evaporated. Just when it has finished evaporation, then only the temperature is going to be 100 degrees centigrade only. That means after saturation, the saturation temperature, saturation is the lowest temperature. Okay, saturation, if this is the vapor dome, here comes the saturation temperature. Saturation temperature is nothing but it is the temperature, lowest temperature, where all of the substance is converted to vapor. Okay, it is the low. If you heat that more, you will get superheated vapor. Okay, but at saturated temperature is the lowest temperature where you can get all vapors without any liquid. Okay, that is known as saturated temperature. So even if this water gets completely, even one particle is remaining, immediately after that particle is going to get evaporated, immediately after the temperature is going to be same only. Okay, so that means saturated temperature is the lowest temperature where you can get all vapor without any liquid. Okay, so the change in entropy for phase change is going to be latent heat divided by saturated temperature. Okay. Okay, so the next question is liquid water enters an adiabatic piping system at 15 degrees centigrade at a rate of 8 kg per second, and if the temperature is increased by 0.2 degrees centigrade due to friction, find the entropy generation within the pipe. Okay, so they have said what? They have said that in a pipe water is coming in at a rate of 8 kg per second while the temperature of it was 15 degree centigrade, and while flowing due to friction the temperature is getting increased by 0.2 degrees centigrade. So we need to find out what is going to be the entropy change. Okay, so if we want to find out the entropy change, the first thing we need to know what is going to be the initial temperature of the water. So what is the initial temperature? Initial temperature they have given it as 15 degrees centigrade. Okay, 15 degrees centigrade, which is equal to 288 Kelvin. Okay, this is 288 Kelvin. Now what they have said that the final temperature is increased by 0.2 degrees centigrade, that is 288.2 Kelvin. Okay, they have given degree centigrade, but whenever this is difference, okay, difference or rise in temperature, it is not going to make any difference whether it is degree centigrade or Kelvin. So I am directly writing 0.2 degree centigrade in terms of Kelvin. Okay, that means if there is difference in temperature, it doesn't matter whether it is in degree centigrade or Kelvin. Okay, so I have directly written this. So what is going to be the entropy generation or entropy change here is going to be S2 minus S1. Okay, so that means what is going to be S2? So S2 minus S1 is del S. Okay, now this one, suppose we are taking only the water of per second. Okay, in 1 second whatever water is coming in, so this we can say that this is a finite temperature body. Okay, we can say that this is the finite temperature. We can just take the 8 kg mass and then we can evaluate. So this is a finite temperature body having initial temperature is this, final temperature is this. Okay, now for this we have derived one formula that for final temperature this is going to be m into c into ln of T final by T initial. Okay, so this is going to be our formula for entropy change. Now mass rate they have given, okay, mass flow rate they have given as 8 kg per second. Okay, and C, specific heat. Okay, the specific heat of water, they have given water. The specific heat of water we need to remember it as 4.2 kilojoule per kg Kelvin. Okay, 4.2 kilojoule per kg Kelvin, or we can write 4200. You can write 4200 joule per kg Kelvin. Okay, so I am writing 4200 ln of T final is what? 288.2 divided by initial temperature is 288 Kelvin. So if you calculate this, the final temperature, final expression of the final value of del S or the entropy generation you are going to get is 23 watt per Kelvin. 23 watt per Kelvin. Generally, the entropy change is given as watt per Kelvin. That's why I have written 4200. 4200 I have written because it has a unit of joule. Okay, and in place of mass there is a kg per second. Okay, and watt is formed by joule per second. Okay, so since I have to find the answer with the unit of watt per Kelvin, that's why I have taken joule per second. Per second is with mass, okay, kg per second, and the C is having a value of 4.2 kilojoule per kg. If I had taken 4.2, it would have been kilowatt per Kelvin, okay, because there is kilojoule, and kilojoule per second is going to be kilowatt. Okay, so I have written 4200 because I need the answer in watt per Kelvin. Okay.